All right. Hello, everybody. Can people hear me? All right. Hello. Can people hear me? Say something in chat if you can hear me, please. Okay, good. All right. So I will be going over divide and conquer paradigm and problems from problem set 2. Feel free to ask questions in the live chat as I go along. Otherwise, I will be trying just going through the thread on Piazza. So let's get started. I'll start off with problem 3, which is the problem about finding the closest pair of points in a plane. And this is suggested to use the divide and conquer paradigm, similar to how we did maximum subarray. And the question was asked to go over part B, which is designing the algorithm, because it's a bit confusing. So to start off with, we have a plane and there's a bunch of points, and we want to find the closest pair. And the idea is we are to assume that the points are already sorted according to their x coordinates, that we're going to divide by the middle of the array and then conquer the points, all the points on the left and all the points on the right separately. And then we'll have a, sorry, is it out of focus? I tried this yesterday and it pretty well. It was much better than my my computer webcam. Is it in focus for other people? That's unfortunate. Oh, okay. Good. Perfect. Good to hear. So we start with an array. I'm going to call the array X, and this is the points sorted by their x coordinates. So x2, y2, and then we're also going to be, it's going to be helpful to also sort by the y coordinates. This will help us in the combined step when we have to do the pair of points that might cross the midpoint. So sort y of x Okay, so we'll get to the combined step, which is the hardest part. So we start off, and so let's write it out. Let me put this in the middle. Define closest pair recursive and this takes in the X array, which is all of our points in sorted in the X coordinate in the X axis, and the Y array, which is the same points sorted in the Y axis. And then base cases, we have if there are only 2 points in the array, then the closest pair of points is those 2 points. So we want to return return x0, x1, and we'll say that we have a function that we can call to get the distance between 2 points. So that will be distance between x0 and x1. Yeah, I'm sorry if it's a little out of focus. I'm just doing this on I'm not really set up for streaming, so this seemed to work out better than doing it on my computer, but it's still not going to be perfect. It's just streaming straight from my phone. All right, and then if there are 3 points in the array, then we use the brute force, which you just check every pair of points from part A of the problem. And because there's only 3 points, that's fine to check 3 pairs of points and figure out which one's closest. And so now we're getting into the meat of the algorithm, which is the divide and conquer. So the divide step, so n equals the length of the array. So we are going to find the midpoint of the array and then call this algorithm recursively with the points in the left and right side of that. So mid equals n/2. So we're dividing it by points to the left and the right of the middle on the x-axis. So for the x array, we can just slice the array to the left and the right. For the y array, we have to do comparisons of the x coordinates. So y and my pseudocode is all Python style, so have some like list comprehensions. So yi. So we're just iterating over the entire array. If yi 0, so if the x coordinate is less than the midpoint, so x mid 0. All right, so this will put everything that is to the left of the midpoint on the x-axis in one array for y, and then we will do the same thing for all the points that are on the right side, and that'll be, I'm not going to write it out for time, but it'll look just like this, except this will be a greater than or equals. Do I have an option here? I will. Yeah, I will. Let me just grab some non-lined paper so I can write bigger, and then I'll also scan everything after. I can scan all the sheets that I'm writing on and upload them after the office hours is over. So let's see. Let me try putting this just up so we can make it bigger before I take it off screen. Oh, that is really out of focus, isn't it? All right. Well, okay. So I'm not going to copy over what I had on the other page, but so we left it. We have left y and right y, and then we are going to do the recursive call. So we get left min 0.1, left min 0.2, and left min distance is equal to our call to closest pair recursive of x from low to mid. Oh, something I missed in closest pair recursive. Oh, never mind. I didn't miss it. I just what I'd written up earlier, I had forgotten to write out. We just x, all of the points to the left of the mid index are here, and then left y, and then right min 0.1, etc. It's the same return, is equals closest pair recursive of all the points. Nope. All the points to the right of the midpoint and right y. And so that's it for the conquer step. So now now I'm going to talk about the combined step, and this is where it gets a bit tricky. So I'm going to draw our points again, and in this case, I'm going to say that this right here is the midpoint, is the x coordinate of the midpoint of the array. So that is x mid's x coordinate. So now we have points on the right and points on the left, somewhere around here. So we have three cases. Either the closest pair of points in the whole array is to the left, in which case it will be returned by this recursive call, or the closest pair of points is on the right, in which case it will be returned by this call, or the closest pair of points crosses this barrier somehow. And the key to making divide and conquer work for this algorithm is figuring out how to check the least number of points that cross this barrier, so that you will find any that are the closest, but you don't have to check all the points on the left with all the points on the right, because that wouldn't be much faster than just doing an exhaustive search brute force like you did in part A. So the key observation here, I'm gonna list out a few things before we get into the actual algorithm. So let's call, we want the minimum distance of a pair of points that are both on one side or the other. So min of left min d. So I'm going to call that delta. So, and the first thing to observe is that from this midpoint, you only have to look delta to the right and delta to the left. Because if there's some point over here where the x coordinate is more than delta away from the midpoint, any point, any point on the left of the midpoint will be more than delta total distance away, because it's already more than delta away on, it's already more than delta away in just the x-axis. So we can throw away everything over here and throw away everything over here. So this limits us to just this band around the midpoint. And so this gets us part of the way there, but we could still have lots and lots of points that are close together in x, but not close together in y. Brian, I just saw your message. I think that's what I'm talking about now. I'm not sure when you asked that. Did you have something that I'm not addressing, or should I? Okay. All right. So this is key number one, is this delta. And now I'll go to another sheet. Key number two. So here is our midpoint, and we go out delta on either side. And now now we're going to look at it for a specific point. So say this point is the one that we are considering. And so we need to check all points that could be within delta total here. Now, so the next observation is that for this particular point, we only need to look delta above and delta below. So, and again, this is something that you have to do for each point. You've already checked that recursively, but you still have to check all the points on the y-axis. But for each point, you only have to check points that are within delta above and below of it. And now the third key to observe is that I'm going to draw these grid lines that are delta over 2 apart and make this box that has 8 grids in 8 boxes in it. We'll make this one in that box. And now the last kind of key observation before we actually get into doing the combined step is that in every one of these boxes, there's at most 1 point. And why is this? Well, so this side is delta over 2. And I should have done this over here where I didn't already have a delta, but What? Rachel, did we lose the internet?
Yeah.
Crap.
Yeah.
Um, actually, I might still be streaming on here. I'm going to keep going and hope that it's streaming and doesn't use too much of my mobile data. I just lost internet on my computer. Um, so this is also delta over 2. And so the key observation is that then, so I'll draw, this is a delta over 2 box. So if there's a point in the very bottom left and a point in the very top right, they are this distance d equals square root of 2 over 2 times delta, which is less than delta. And because every point that is in this box is on the same side of the midpoint, then that means that there can be at most one point in this box, because remember, delta was the minimum distance of any pair of points that doesn't cross the boundary. All right. I think we have it back. Okay. All right, so let's see. What this means is that there, in this window, after we throw out all of the points that are to the right and to the left, we have 8 boxes above. For a given point, we have to look. There are at most 8 points above that we haven't thrown out already, and at most 8 points below. We could maybe make this a little tighter, because obviously this d being less than delta, we could grow those boxes a little bit, but it's much easier to work with in this with delta over 2. So that's going to let us filter for each point we look at. We only have to check the 16 closest points to it by y. So I'm going to go in and write up this closest pair crossing algorithm. I'll switch to another sheet of paper for that. So closest pair crossing x, and in this case, and we we pass in the delta. Now my pseudocode's getting a little out of order, because I'm trying to show the key points at the same time. So this is where we'll be doing that approach that I just described. So let's see. So we redo the calculation of the midpoint. So len x over 2, and now what we want to do is we want to filter out, so yd, so